So this is going to be our first flip class video for this course. We're going to start off by talking of functions of several variables. That's essentially what this course is going to be about. So we're used to looking at functions of just one variable. So this is what we've encountered in all of our previous math classes for the most part. In particular, Calculus 1 and Calculus 2 dealt with functions with one independent variable x and a dependent variable y. Of course, we can use different letters for these, but the point is you're inputting one variable and you're outputting another variable based on some function. So we can have our functions can input whatever, it's really just a rule, but for us, and for the most part in calculus, we were inputting a real number and outputting a real number. So the real numbers here are denoted by this boldface R, and we write f colon, so then the R there is our domain, and the R on the other side of the arrow there is our range. So f inputs a real number and outputs a real number. Of course, the domain doesn't have to be the entire real numbers. We're just writing it here for simplicity for a general function. So we can easily have multiple independent variables. So if you've encountered math in other classes, like real world classes where you're looking at applications, you know that most things in the real world don't depend upon just one variable. There's usually many factors at play in any process. So that's what we need to come to grips with in this class is we know how to do calculus with one variable. We need to know how to do calculus with multiple variables. So let's see an example where a function might take in multiple variables. So let's let S be your score in a class. And let's suppose for that class, there are several things that go into determining your final score. So you have a homework score H, an in-class grade C, you have two different midterms, M1 and M2, and then you have a final exam given by X. And now your syllabus should tell you what the function is that determines your final score. So for example, maybe we have this formula where S is G, which is a function of H, C, M1, M2, and F, which is final exam score, not X. And so then for our syllabus, it says the homework score is 20%, the in-class grade is 20%, midterm 1 is 15, midterm 2 is 15, and then the final exam score is 30% of the grade. So we can see our final score depends upon 5 variables here. So how would we use a formula like this? Well, let's suppose you have a 95% on your homework, and 80% on the in-class grade, 75% on midterm 1, 83% on midterm 2, and 72% on your final. In that case, your overall score would be given by this formula here. So we plug in 95 for H, 80 for C, 75 for M1, 83 for M2, and 72 for F. And then in the formula above, you just replace those. So it's 0.2 times, well, H is now 95, plus 0.2 times 80 because C is now 80, and so on. And so if we calculate that out, we see the final grade, or the final score for the course is 80 points. So we have 5 input variables and 1 output variable. So the way we write this now is our domain is inputting 5 variables, so we write r raised to the 5, and our output is outputting 1 variable, so we just write an r there. And now, of course, our domain isn't all of R5, it's because we can't plug in any number for these things. For instance, your homework score can't be a negative 20, at least in most classes we don't use negative numbers for homework scores. So really you're looking between 0 and 100 for each of these. But it's just easier to write the R5 there for now, just to kind of indicate that we have 5 variables inputted and 1 variable out. Let's look at another example with just some functions we're used to here. So let's let f of xy be x squared times cosine of y plus sine of y. So notice we're inputting 2 variables here and we're outputting a number. So if we look at this, if we plug in 2 for x and pi over 3 for y, everywhere on the right hand side there's an x, I put a 2, and everywhere there's a y, I put a pi over 3. So I get 2 squared times cosine of pi over 3 plus sine of pi over 3, which simplifies down to be this number here. So it's not so hard to evaluate functions of multiple variables. It's just like functions of one variable, you just have more places to put things into. So now, as I said, here we have 2 output variables and 2 input variables and 1 output variable. So f goes from R2 to R. So let's look at another type of example here. So in this case, we're going to have one input variable t, and we're going to have two different outputs. So notice we input t and we output the ordered pair cosine of t and sine of t. So one input variable, two output variables. So if we were thinking about what we're getting from this, this is really just the familiar circle of radius 1 centered at the origin, because we're inputting t, which we can think of as an angle, and then cosine t sine t is just the xy coordinates on the unit circle. So for now, we're really only going to be focused on functions that input multiple variables and output one variable. But later in the course, we will come back to functions like this because we'll have curves in space, say that a particle is traveling along, and we'll need to represent those curves with functions that input one variable and output two or three variables. But for now, we'll focus on numerous inputs and one output. And one of the reasons for that is we can graph those types of functions. So our brains can only visualize three space, so the most we can do if we want to graph something is we can have a function that inputs two variables and outputs one variable. So if you think of what you graphed before in Calculus 1, you inputted one variable and outputted one variable. So we had one variable for the x-axis and another variable for the y-axis. Now for us, we're going to have two variables for the input, so x and y, and then we'll want one variable for the output. So that gives us three space. And so we have to introduce what do we mean by three-dimensional space. Well, we can kind of already see it here on the right. But what we're going to do is we're going to look at the xy plane that we're familiar with, and we add another axis to it, the z-axis. So you can see here we have an x-axis, a y-axis, and a z-axis. And wherever I'm writing the x, y, and z, those are the positive directions. So if you move towards the x there, you're moving in the positive direction for x. So there is something that's a little different here we have to be careful of. There's an orientation, and we want to make sure everybody's agreeing with the same orientation so there's not random negative signs between different people's work. So to get our correct orientation, we're going to use what's called the right-hand rule. So to do this, to get the correct, whether I should put the z on the top or the bottom there for the z-axis, you put your right hand along the x-axis with your fingers pointing, start it at like the origin and point your fingers towards the x, where the x is on the axis. Now curl your fingers towards the y-axis. So you should actually be doing this to see how this works. Curl your fingers towards the y-axis, and now let your thumb point up. And the direction your thumb points when you do that is the positive z-axis. So that's how we get our orientation. And here's a graphical representation of the point 1, 2, 3. So we've gone 1 unit in the positive x direction, 2 units in the positive y direction, and then 3 units in the positive z direction. It's a little hard to see here on the graph, but just think of going 1 in the x direction and then 2 in the y direction. So maybe I'll get my little cursor here if it shows up. We go 1 in this direction, and then we go 2 in this direction, and then we go up. So this is sitting over this point here. Below it in the xy plane, that would be the point 1, 2. Now, a few things that show up a lot in this course. One of them are planes. So in three-dimensional plane space, planes are given by equations that look in this form. So it almost looks like if you got rid of the b times y minus y0, this would look like a line. But in 3 space, this is actually a plane. So you have z0 plus a times x minus x0 plus b times y minus y0. And here z0, a, b, x0, and y0 are all just constants. In other words, they're just numbers. They aren't changing. And we'll see later in the course what each of these terms actually means, the z0, a, x0, and y0. But for now, we can just see this plane over here that I've graphed. This is the plane z equals 2 plus 3 times x minus 2 plus 5 times y plus 1. So no need to worry about how I came up with this graph from that. For now, we're just looking at some examples of functions of multiple variables for now. Another example we'll see a lot in this course are paraboloids. So one of the reasons we like this is it's fairly simple to graph a paraboloid. So in this case, these are functions of the form z is equal to a plus bx squared plus cy squared. And so here's a picture of a paraboloid. They kind of look like bowls, either upside down or right side up, depending upon the signs in front of the x's and the y's. But here, this is the paraboloid 10 minus x squared minus 2y squared. So you can see if you put in x equals 0, you get a parabola 10 minus 2y squared. And similarly, if you put in y equals 0, you get a parabola 10 minus x squared. So when we talk about how we can graph some of these things by hand, we'll be talking about things like that, where you set your variables equal to 0 or 1 or something like that to get kind of an idea of what's going on. But for now, we're just looking at pretty pictures for this section. Here's another example. In this case, we have z is equal to sine of x. So in this case, we only have one input variable and one output variable. But if we want to graph this in 3 space, we have to take into account the y variables as well, even though they don't show up in our equation. So what that means is we could just graph this function z is equal to sine of x in the xz plane, and then kind of just pull it sideways through the y variable direction, because y, it doesn't depend upon y at all. And you see, if you look at this from the side, you'd have the normal sine graph you're used to, and then you just kind of extended it in the y direction in each direction. So far, these examples we've done so far are ones that later in the course we'll be able to graph these ones by hand. Um, but the next one's not so much. So if you remember from calculus, often you either graphed things that you knew what the graphs already looked like, or you used a calculator or some mathematical software to do the graphs for you, because it's just really not so easy. If I give you some random function for you to figure out what a graph looks like, it's really useful to have computers to do this for us. And it's even more so the case when we have functions of multiple variables. So in this case, if I take a fairly simple function, just z is equal to sine x plus cosine of y, we already get this fairly complicated looking graph where it looks like things like bubbling water or something here, where it's going kind of all over the place. And so you can imagine how much more complicated this can get if you get much more complicated formulas. So we'll be using Mathematica in this course to help with some graphing and visualization as we go along. But that's it for our first introduction to functions of multiple variables. We'll be seeing in the next section how we can look at two-dimensional representations of this three-dimensional data. And it might seem like that's something you've never seen before, but we're going to see you have seen those before when you've looked at weather maps or topographical maps or things like that. That will be in our next section.